We're now going to start in Part 5, which is one of the larger tomes dealing with radon issues. It deals with the protocols, and I think I've summarized the protocols in a fairly reasonable way that makes it easy to remember most of the details. Now, before we get into the text itself, I have asked a representative from the Pennsylvania DER, Mr. Bob Lewis, to come down and demonstrate to us the different types of equipment to which these protocols pertain. And I think after we look at the equipment and see how they operate, we'll have a better sense of why the protocols are written the way they are, and therefore they will be more easily remembered. So if we could move now to another studio to take a look at the equipment that Bob has brought over. It's a pleasure to have with me this morning Bob Lewis from the Pennsylvania Department of Environmental Resources. His office has been gracious enough to ask him to come down and demonstrate much of their equipment for doing radon measurements. So Bob, welcome to the studio. And I think the first piece of equipment you're going to show us is the Radon EPERM unit.
Correct, yeah.
And so why don't you just show us
Thank
what
you very much.
here.
We're certainly glad to come up here and try to enlighten some of the radon industry and some of the techniques that are available to them.
Great.
This is the EPERM system, EPERM standing for Passive Environmental Radon Monitor. And it's basically a radon detection system as opposed to a working level type system. And basically the crux of their system involves this little chamber here. Mm-hmm. And all that basically happens here is that you take this into the house, basically place it as the protocols, EPA protocols specify, and you open this cap as opposed like this. This is in a closed position. Right. This is basically in an open position like this.
Once it's open, now it's starting to measure the radon concentration.
Correct. Right. The gas in the air then is diffusing into this top here where there's some holes that you can't really see. Mm-hmm. The gas basically diffuses inside this chamber where it creates ionization in the air.
Right.
The second part of the system here is the actual electret itself.
Okay. Now I notice that this electret is black in color, effectively. Is that significant of anything?
That's not particularly significant at all, no.
Okay.
This electret initially has a charge on it. Mm-hmm. Mm-hmm. And before you make the measurement in the house, you use this, which is basically just a voltmeter here. Okay. And this is used to measure the charge on this device. Okay. So
this comes with a certain amount of voltage, what, 500, 600, 700 volts perhaps?
Correct. Usually starts out about 750 volts.
750 volts, okay. And what do you do? Just lay it right on the
Right, you can basically lay it on here. Probably first what you would do, however, in the office or the laboratory is you want to check out this meter by using some standards, which they supply to you also.
Okay, so that comes with the kit? Correct. Yeah, and my understanding is when you buy the EPERM, you can buy just the chambers, of course. Correct. And then you could send can I open this?
Yes.
Okay. And then you could send just these electrets back, and they'll read them for you.
I believe they do that also.
And they have a little, you don't have to send the whole chamber back, they have a little cover that
yes.
that you can use to send back. So you brought that too.
There it is.
Okay.
Which they would certainly recommend you to put on.
Oh yeah, right, right. And you don't want to touch the electret at all.
Definitely, this is very, very sensitive to touch or dust, for instance, also.
Right. So typically, when it's ready to send back, if you didn't have the electrometer, the voltmeter here, you just mail this back. Correct. Right. And they read it and let you know what the radon concentration.
Right. And as soon as you basically put this cap on, then your measurement period is stopped.
Right,
so then that'll be stable until they read it.
Right. But now, if you have the electrometer yourself, and you can buy that as part of a kit, right, then you can read these electrets on your own.
You can read them yourself.
And then determine the radon concentration right to the picocurie per liter, right?
Exactly. They give you a little handheld Radio Shack calculator that you can make a calculation on. You can do it by hand. You can do it in your personal computer or whatever.
Right, okay.
And it's basically just done by initially just taking the standards that they also supply for you.
Okay. And that's now these standards that are checked that the voltmeter is operating properly.
Correct. This has a specified voltage that they will tell you. So this will be maybe 230 volts, say. Okay. And you should put it on here, and that should be reading 230 or whatever the standard actually is.
Now, can we take this out of its case here?
Certainly.
Okay. And if I hold it like this, to activate the voltmeter, do I just push this lever down?
Correct. Actually, first we should take that off and just check the zero on this thing, which you do by basically placing something like that on.
Okay, so we have this here, and then, and what do we get down to?
And you place, and then it basically shows a zero, and I would do it one more time also.
Okay, let me let it go off.
And then go down again.
Does it take a long time to go off?
No, that'll stay like that. You go.
Oh, I see.
You want to do that again so that you duplicate that measurement.
Okay, all right.
Now I try it one more time so that you got a different value than initially.
Yeah, what did we get there? I can't quite read
2.
that. 2, okay. 2 volts.
Try it once again.
Okay. All right, so now we have a 0 and 2 2s.
Okay, try it once more.
Okay. Let me just maybe...
We had a charcoal. You might try that. Okay. Some of them do that. Some of them don't zero. Ours, for instance, at the office, it stays at 1.
I see, okay.
But that's not critical because all you're looking at is a difference in voltage.
Right, right,
So
right.
if it reads 2 now, you just want to make sure that it reads 2 when you bring your
you're
device
done.
back in
Right.
from the
Otherwise,
field.
there'd be 2 volts unaccounted for.
Right,
Right,
correct.
okay, okay. But, all right, let's assume that it reads consistently 2.
Correct.
As it has started to do now. Okay, so now what do we do next?
So then you basically would put the standard on and make sure that that read as was specified in there when they
Okay.
sent it to you.
And what do we think it's supposed to be?
I don't know offhand.
Oh, all right. Well, I guess we'll find out just by turning
Right.
this on, right?
Which number is that?
This one is 833.
Well, it was 269, but that was in 590.
1990. Okay,
So it's
well, let's see.
probably lost some since then.
What's it reading there?
264.
264, all right.
So it's lost 5 volts.
It's lost 5 volts.
3
but
years. But it's been
okay.
3 years, so that's
Right.
understandable.
Right, yeah, that seems reasonable to me, too. Okay, okay.
So that basically just gives you an indication that the voltmeter is working correctly.
Okay,
And after you do that, then you can measure the actual devices that you're going to take out into the field.
okay, so now what would have happened is we take the chamber out into the field, and then we expose it
Correct.
by opening it up this way, and we leave it out for whatever number of days we want, and I understand there are short-term electrets and long-term electrets, right?
Right. The basically designation is most of the long-term ones, as far as I know, all of them are red with a red label here, as opposed to the short-term ones, which
Okay.
have blue labels.
All right. Can we see this label down here at all? I don't know if we can get, oh yeah, there it is. And I think you can see the blue quite clearly there. I'm watching it on the monitor, I can see that that's blue. And the other one is in red.
Correct.
And one of them represents a short term and the other represents long term.
Right, and the basic difference that I'm aware of is just the thickness of the electret itself.
Right, right, okay. All right, so then, we finish the measurement in the building we're in, and we seal this, and then we pull off this electret, and we measure we just put it on here.
Correct.
Like that, and then activate the voltmeter, and we read whatever the voltage, currently reading 403 volts
Right.
on that device. Okay.
And then you'll have a pre-measurement and you'll have a post-measurement. And then when you have those two measurements and you have the time difference, then you can calculate the concentration of radon in the house.
Right. So all you need then is the pre and post voltage and the amount of time that it was exposed.
Need the time. And there's one additional factor, and that's a background subtraction factor that they use.
Okay.
Gamma radiation, which this micro-R meter measures, can also interact, cause ionization in these chambers.
Right.
So that's something you should be aware of. And when they send you their kits, which is one very good aspect of the EPERM system, they send an entire notebook here, and has introductions and has their different products and prices and so forth. And also one very good aspect of that package is it sends you a quality assurance plan.
Okay. So it tells you how to operate the system.
Basically tells you how to operate it so you're getting accurate and reproducible results.
Okay. All right.
This is required, quality assurance plan, by the state. It's also required by the EPA in their radon measurement proficiency program.
Right, in the RMP.
So this is a big plus that many companies that supply this instrumentation don't have.
Sure, and this is no minor document.
Oh, no.
I mean, looking at this, it's probably 50 pages or so.
It would
takes
quite a long time to write a quality assurance program.
Sure does, sure does. They've done a good job on that.
Yes.
Now, let's talk about the gamma radiation. The gamma radiation while it's not connected at all to the radon concentrations whatsoever, the gamma radiation is due to other sources of background radiation.
Correct. There's corrosion of soil and rocks and sometimes the building material of houses.
Okay, and typically, even if you don't know what the gamma radiation is, you do take it into account by standard background terms. In other words, you subtract off, I've forgotten the exact numbers, but I think it's something like 0.8 picocuries per liter for every 10 microroentgens of gamma radiation. Is that right?
And they quote that in their manual.
They tell you how to subtract it off.
Yes, and it is state specific. So Pennsylvania has a certain value, Maryland has a different value, and so on and so forth.
Okay, oh, that's interesting. So the gamma radiation in different states, on the average, is expected to be different.
Right.
Right, okay.
Because of elevation and different uranium-bearing rocks and so forth.
Right. So even if you don't have a monitor of this type that measures gamma radiation these devices are still perfectly usable.
Still can give you a very good measurement.
Right. Now, if you do have one of these devices for measuring gamma radiation, then you could use that instead of the standard terms.
You could use that. You would certainly get a slightly more accurate result. The difference would probably be not too substantial unless you were in a house that had very high gamma, 20, 40, 50 microarc per hour.
Right. And in that case, the problem may be much more than a radon problem.
Could be.
Yeah, right. Okay. All right. Well, that's a pretty simple system, and I did jot down some prices, and I think the EPERM unit is going to run somewhere around $2,800. I'm not exactly certain of that price, but it's in that order, and for that, I believe you do get a number of these chambers.
Correct. You get several of the chambers. You get the reader, the instruction manual, QA plan, standards. I think you even get a videotape that goes through
it shows you how to use it. Yeah, I
something
have
of
seen
that
the
nature.
video. Right,
Yes.
right. I just want to show one more thing. If we can take a look at this, when it comes to activating it, here we go. If it comes to activating, all that you do when you pull this little lever down is you just open the door so that the voltmeter measuring device becomes open to the electret. Otherwise, you see it's shielded and closed. Okay, so I just wanted to show that one extra feature. Okay. Now, gee, I do want to talk a little bit more about this. If we open this up at the bottom, I think you can see perhaps the plunger here. Can we get into this plunger at all? There, let me see here. Well, it's very hard to see. It's black and black, and but if I open this up, I think you can see there's a little motion inside, and the plunger moves back towards the top, opening the electret. The electret is covered by this. When this plunger is down like this, the electret is covered by the bottom of the plunger, which I'm afraid we are not able to get a particularly good shot on. And then there's a piece of filter paper that I see in there, Bob.
Correct.
Right? And what's the function of the filter paper in there?
Well, because this is a radon measuring device, you don't want radon progeny or the radon daughters to come in here and interfere with that measurement. So that filter paper basically will filter out all those progeny, and the only thing that is in there to diffuse in there is the radon gas itself.
Right. The progeny are all solids.
Correct.
And so the filter paper tends to subtract those out.
Solids, plus they're usually attached onto some sort of aerosol particles, smoke, dust in the air,
right.
Which is in this filter paper is very efficient at collecting those things.
Okay. So primarily you get just the radon gas or any other gases in the room.
Any other gases also, certainly.
Into the chamber. Okay, that's great. All right, let's take a look at another piece of equipment here.
Or maybe just a couple additional things with the EPERM system.
Oh, okay.
Just some of their sort of side points is they have different detectors for different things. They have a range. This is a long-term range detector that extends the range of even their long-term red label farther.
Right. Now the red label is good for about a year?
About a year. Some people can make measurements for the year. This, because of the reduced volume here in this chamber, you could go for maybe even a 2-year measurement if you wanted to, or if the concentrations were too high for this, that it would burn this electret out, then you might have applicability to use
Now when you say burn the electret out, you mean lower the voltage on the electret down to below some value that's
beyond
useful.
the usable level, which I believe they quoted about 200 volts. Once it gets below about 200 volts, and you don't want to you want to repeat that measurement.
Right. Oh, now that you've said that, something else occurs to me, and that is that you can deploy this detector into a home, expose it, and of course, you read the voltage before, say it's 750, and then after you've got it out for whatever number of days, you put it out maybe 10 or 20 or 30 days or whatever. You seal it up again, you read the voltage again, now it reads, say, 700 volts, that is, it's dropped from 750 to 700. You can use this chamber and electret again, is that right?
That's a very good point, sure.
Starting off with your initial voltage of 700, maybe it'll drop to 600, and as long as the voltage doesn't get down around 200 volts, you just continue using this over and over again. So one chamber might be good for half a dozen measurements, perhaps a few more as well.
That certainly is one of the advantages of that device. It certainly also points out maybe one of the disadvantages, that if you happen to put a low or a short-term chamber in a high house, you would burn it out and then you would lose that measurement completely.
Oh, right.
And then you would have to go back in with maybe say a long-term chamber to do the measurement again.
Okay, right. Yeah, so that would be a problem on the opposite side of the coin.
Yes.
Okay. And
some of the other things you can do with the EPERM systems, you can actually make radon and water measurements. Basically, they just use this. This is going to be something certainly more important when EPA finally sets their standard for radon and water, which we don't know when at this time.
Yeah, although I've heard 1996 is going to be a regulatory limit, and that limit will be about 300 picocuries per liter.
That's the limit we hear on the grapevine, so I
Yeah,
don't know
right.
if it's going to sell.
Right.
And basically, you just, from the spigot, use this little vial here and fill that up, and then cap it, and then it's just,
This looks like a mayonnaise jar.
that's about what it is. You basically just put the vial in here, and the water spills over like that, and then you take one of your electrodes with the E-perm chamber and put it in like that.
Oh, I see. There's a little
And
hook
it's
in it.
exposed in there.
Oh, no kidding. So then,
And like that. So basically the radon just off gases from the solution
water.
out of the water, and it exposes the electrode, and you can get an actual radon and water measurement by
I
this
see.
technique.
In other words, by knowing how much radon and air is in the chamber, is in this jar, which is monitored by the E-perm unit,
Right.
we can calculate backwards, so to speak, into the radon and water concentration.
Yes.
That's a nice idea, nice feature.
So that's one of
nice
the things.
feature. Yeah.
And something else that probably is not too applicable to most of the radon industry is they can make, with this sort of a prototype device of theirs, they can make thoron measurements.
Okay. Right.
We have not done many thoron measurements ourselves. Basically, the chamber is the same as these type of chambers, except they have cut some holes in here to allow the gas to diffuse in more easily to the chamber, since it has a shorter half-life than radon.
Right.
The applicability, once again, in the radon industry is probably not very great, but it is available.
Okay. Thoron being one of the confounding parameters of making a radon measurement. At the moment, it seems it would be pretty unusual for thoron to complicate a radon measurement, but that's always a possibility. And I think perhaps maybe a year or two, maybe a few more years down the road, we might see some protocols on how to deal with that kind of issue.
I wouldn't be surprised at all.
Yeah, but at the moment, I don't think there's anything that we are regulated to do in any case to sort out the thoron issue.
That's correct.
If it is an issue at all. Okay. All right. Is there more? This seems a quite capable instrument.
I think that's about it, at least that I brought from the E-perm instrumentation.
Okay. All right. Let's let's move on to another instrument now. Now, Bob, you've set up the Ludlam continuous working level monitor here, right?
Correct.
And this is for doing grab samples.
Yeah, this is not a continuous working level monitor. This is just
Okay.
based, okay. This
Right,
is just a
thanks.
scaler and a full multiplier too. This is a detector basically for looking at grab working level samples.
Okay, so here we're going to go into a house. This device is used to go into a house, take a few minutes sample, and then analyze that sample.
Yeah, typically we took about a 5-minute air sample in the house, usually in the basement, and then in about 40 minutes, anywhere between 40 minutes and 90 minutes, we could analyze the sample on here and have results within an hour and a half or so to the
Okay.
homeowner.
Right,
So
okay.
it's sort of a quick and dirty type of technique.
All right.
Probably not used very much anymore today because EPA protocols really aren't even allowing this to be used. But it was a technique that was used quite a bit in mines and also the homes when we were initially
Right,
sampling in the Reading Prong area.
Yeah, now you can't use it for the purpose of delivering to the homeowner a measurement upon which the homeowner will base whether or not to have mitigation performed.
Correct. You should not be doing that.
Right, but you could use it if you were a mitigator, for example, and you wanted to know if, gee, what's the radon concentration in a sump hole, for example. Maybe that's where it's real high.
It could be used for that. They probably use another technique we'll show later, more like just grab radon samples. It's much more applicable for that, but you could
Okay.
use it for that.
Okay. Well, let's take a look and see how this one operates here.
Well, this is basically just what they call a scaler here. This is all that just registers. This has a timing mode, and it registers the counts in here. And you can just basically demonstrate the counts by putting a standard into this. This is actually the detector here. This is a photomultiplier tube, and the actual detecting medium is zinc sulfide.
Right. So what happens is, typically what you would do, though, is you would go into the house and you use a pump of this type.
Correct.
And you draw air across. You have a.
We have a filter here.
Okay.
This is just the filter holder assembly here.
Right.
And you would place a filter in the filter assembly like such,
Right.
and this just maintains it in there.
Okay. And what we're going to do is draw air across that filter.
Correct. That's
and
what
then
that's what the grids are there for. That indicates where the aerosol particles are being deposited,
Okay.
so you know the correct position to place it in your
Right.
detector.
Yeah, you wouldn't want it upside down.
No.
Okay.
And just place it in there, and then just a matter of
Okay. We can probably hear that.
turning that.
Yeah. And so that will sample for however long we allow it to sample.
Correct.
Let's say 5 minutes.
So the air particles are just being drawn onto that filter as we
Right.
speak.
Okay, as we speak. And then after 5 minutes, we would stop this.
Correct. Just turn it off,
Okay. And
and then the filter just
Right.
Taken out of there. And once again, it's critical that you place it this side up.
Yep.
So the alpha particles are traveling up towards the detector.
Right. So what we have on this now are actually the solids, so that would be the daughter products of the radon and
Correct.
not the radon itself.
Correct.
Okay.
And then you just basically close this, and the unit would just be turned on by pressing the count button.
Okay.
Now we're probably not going to see anything here because we didn't take anything, but we can certainly demonstrate that by placing a standard in here.
Okay. Now, if we were going to use this kind of device, what are the things we have to watch out for prior to turning it on in a building? Say prior to turning on the pump, the air pump.
Well, probably the two things you want to be doing with this is first you want to make sure you know what the efficiency of the unit is.
Right.
And you also want to know what the background of the unit is.
Okay.
Because those things are critical in the actual calculation of the radon daughter concentration.
Okay. Now we get the efficiency from this standard here?
Correct. This is just a standard. It's thorium-230, and it gives you a known amount of disintegrations per minute.
Okay.
So you basically place that in there.
And we should be seeing
count
some. Oh
this
yeah, we are. We're seeing some action now.
Oh, it's on. Okay.
I don't know. Can we get that on? Oh yeah. I think you can just you can see the numbers running on that. And so we let this run
So we'll count this. We usually count it for 10 minutes.
Okay.
And we can get an efficiency for this unit.
Right. In other words, we would know, for example, the decays per minute on that particular one. I see it in the box is 10,900. So if we were to count for 1 minute and we counted, say, 5,450, exactly half of the decays per minute, then we'd say, well, the efficiency is 50%.
Right.
We're picking up half of all the decays are being picked up by the phototube.
And then that 50% efficiency then is used in the calculation to derive a radon daughter concentration for the house.
Right. I can see how that would work. And then now on that flow meter or on that pump, the things we would check when we turn it on.
That's a good point also. This should probably be checked before you go out in the field. Or we usually, I guess, check it just maybe once a week, just determine the correct flow of this.
Right.
We would use just a graduated cylinder and put a soap bubble through it and just time the soap bubble through a given distance or given volume.
Okay.
And by that you could get the flow rate of the pump.
Right, right. Now the flow rate of the pump goes into the calculation that determines the radon daughter concentration, the working level concentration. Okay. And now, but if I were going to use this myself, then to check the flow, I would simply turn it on, and I notice there is a flow meter gauge in there.
There is one there, yes.
And check to make sure that that is reading approximately the right value.
Right.
Right. Okay. Okay. And now, so one of the other things too is we want to make sure that we have a properly situated new filter in the filter holder for each case.
Certainly, you would usually use a separate filter every time you did a
Right. You have to
measurement.
discard those filters. Absolutely right. Okay. All right. Well, that's a pretty straightforward system.
And this also can be used with a battery so that you can take it out into the field. We have done counting in the car, in vehicles, for instance, because we're out at, 40 miles away from the office. You have no time to get back to the office.
Right, right. Yeah, at the moment we have it plugged in, of course, but yeah, it is also battery operated.
You have to be somewhat careful. These cords can sometimes get a short in them, and if you're jostling it around while you're making the measurement, it's probably not the best idea.
So you ought to stop the car to make the measurement.
Yes.
Okay. And this device, I noticed in my note here, this device, the scaler, the phototube, the scintillating material, and the standards run about $1,500? Is that about right?
$1,500 for
roughly?
probably these two things. Yes.
Okay. And again, these can be used for grab measurements, and they cannot be used to report to the homeowner what their radon concentration would be.
Correct. Since it's just a snapshot in time.
Right. And we know that the... Go ahead.
Because of the fluctuations, obviously, it's not going to give you a very true representative value of the concentrations in the house.
Right. It's not much of an average value. It's a quick grab sample. Okay. All right. Is there anything more on this
I think that pretty much covers this unit.
Okay. Let's move on to the next unit then. All right. Now, Bob, this one here that you put up on the table, this is Everline's working level monitor. Right. And this one we would list as a continuous working level
continuous working level monitor.
I mean, we just let it run for as long as we tell it to run.
Whatever. This is basically the programming unit of the device. This is the detector here.
Okay.
So this is where you do the programming, and you can run it for 48 hours, which would be the minimum sampling time.
I think you can see some of the controls here. I think you have this is the programming pad.
That's the programming pad, basically.
And this is the output.
This is the output.
The data comes out.
This is the actual connection right here, where the reader interfaces with the detector, on-off switch, and that's about all there is to it.
Okay. All right. Great. All right. And then, so it's a working level monitor. That means that, again, we're looking at radon daughters and not the radon itself.
Once again, you are collecting the daughters on piece of filter paper.
Okay, right.
That you're pulling through this detector here.
In fact, anytime you're using a monitor with a piece of filter paper in it, principally, and you're going to look at the filter paper, you're looking at the daughters.
When you're looking at the filter paper, correct.
Right, okay.
The insides of the detector we can certainly show. I guess we should point out this is probably one of the more pricey models, but it certainly, for us, has proven itself to be very reliable.
Okay, and the price is running about $7,000 for the complete
Right.
two-piece kit here.
Right. This is the actual air intake here.
Okay.
And the filter is basically placed inside here, and this has come down. This goes off. And there's no filter in there now, but we would just take this off and place a filter in there.
Okay.
And then when the pump starts, it would draw air through here and then onto the filter.
Right.
And then there's a solid state detector under here,
Okay.
which detects the alpha emissions from what's on the filter paper.
Okay. Now, so one of the things, of course, you have to be careful about in this is you want to replace the filter paper prior to each use, right?
It probably wouldn't be critical if you waited long enough, because it's going to die down. All these short-lived daughter products, within 4 hours, are basically going to be gone. The only thing you would want to worry about is the filter paper becomes loaded and the flow is reduced, and you could have some problems.
Oh, I see.
So
okay.
certainly, I always replace it every time.
Yeah, and I think that would be a good...
For the price of filter paper, there's no sense taking any chances.
That's right. Now, you also, this pumps air across the filter paper, and so there's a pump in there, obviously. Is there a way to check if the pump is having the proper flow rate?
Correct. That's one of the things that I do before. Two things basically is, once again, using the same type of standard, you can put the standard where the filter paper goes and run it through this interface here and check the efficiency of this unit.
Okay.
And you should also check the flow rate of this unit basically just by, this is the pull, that's the hook to the pump.
Right.
And you can hook this up once again to some sort of a calibrated device. We once again use the graduated cylinder to determine the airflow rate.
Or you can just put it on a flow meter and get some measure of
If you had a calibrated flow meter, you can do that also.
calibrated flow meter, okay, all right.
So those two things definitely have to be done because they enter into the calibration factor which you need.
Right, okay. And so now on the paper printout, you get an hourly report?
Correct. You'll get the start date and stop date and the serial number of the unit, and you get each hourly interval that you set it for, a concentration for that particular interval, and then you get an average for the entire sampling period that you've had it in the field.
Right. So you could use this to do a minimum 48-hour measurement.
Very easily.
Right, and let it run. Oh, now this is an interesting thing. If you put this out in the house today, at this very moment, then it's going to take a little bit of time for it to get a reasonable sample on the filter paper. And the first few hours of data may not be indicative of the daughter product concentration in the building. So we have something called the ramp-up time.
Correct.
For a couple hours. Typically, what is the ramp-up time on a device like this?
I'm not sure what the ramp-up time is on this. I usually just throw out the first 4 hours of data.
Okay.
So then I know that I'm into good equilibrium conditions.
Right, right. And then you run it, you'd like to run it 48 hours beyond that if you can.
Yeah.
Right.
I think EPA allows you 2 or so hours if you want to throw a couple pieces of data away.
Right,
to still get your 48-hour, supposed to, meet their R&B protocols.
Yeah, fundamentally the thing to do is if you know it's going to be 3 or 4 hours of ramp-up time, set it for 52 hours and come back after that. Then you know you've satisfied all the protocol requirements. Okay.
I don't know if we could get it to, we could try to interface it, and if there's any data in there, we could dump it or not.
Okay, so it has a memory in the detector part.
Right, because these things basically, this would be placed in the field separate of this unit.
Right.
We've even actually mailed this. We've mailed it up to Andy George at EML to go through his chamber, for instance, and he's placed it, and you just have to time it correctly so that it goes off at the proper time, and he mails it back, and we can pull off the data.
And you then analyze it over here. Okay. Oh, I see. So it fits right on there.
Fits right on there.
There's no cable connection there.
And then just turn it on.
Okay. And
Takes a minute-
something.
takes a minute to
there's
sense.
also a little display here. I can't read what that. Oh, it has the date.
It says connect working level monitor. So, oops, I know
Okay.
why. Let me just let's try this again.
Okay. I could hear the pump start up.
Yeah,
there for a
it goes through a
second.
little self-check.
Okay, so now we're getting some data out of
Getting
this.
some printout.
Initial information.
And then there's just some different routines you can go through. It says set the clock. That's if the present time is not correct.
I see.
And then a parameter file, which enables you to set in calibration factors and flow rates and how long you want it to go for,
Right.
the total sampling time. And there's also a tail that they call it. This has the ability to check for thoron also.
Okay.
We set it for a 4-hour tail, and what it does is the pump stops, but it continues to look at the filter. And it looks at the decay of the daughter products, and by that it goes to an algorithm that
I
can
see.
give you a percentage of thoron if there's any present.
That's darn interesting. That's very, very clever.
But we'll see if we can get a printout. I don't know, data readout, and then you just not enough data, so we lost it somewhere between the line.
Okay.
So.
All right. And so that's pretty much the whole thing.
That's basically it, yeah.
And of course, it can be battery operated.
Yes, it has a rechargeable battery in it, and it also comes with a charging unit. You can, this charges it also here. This tells you basically when your battery's 80% charged, or there's a separate unit you can just plug into in any outlet.
Right. So it's a complete kit in these two small cases.
Correct.
Pretty much. Okay. And so the continuous working level monitor. We have the filter. Oh, and I know one thing I wanted to ask you. The determination of the calibration factor is. Do we do that every time before every measurement?
I honestly forget what the manufacturer says. I always did it. I always checked the efficiency and the flow rate before all the measurements.
Right. It only takes a minute to do that.
Well, it takes a little bit longer than that. It takes maybe a half hour to do both of those two things.
Okay.
And based on my measurements, you probably wouldn't have to, because every time I do it, it's always very consistent.
I see. Okay.
But I have just been, since we don't use it too much, it's easy for me to do it every time.
Right. Okay. Okay. All right. Anything else on this instrument that we should know about?
Not that I can think of at the moment.
Okay. Let's move on to the next instrument then. Okay. Now, Bob, you've set up the Pylon AB5 here, another active monitoring system. And before we get too far into this particular active monitoring system, I want to point out that if individuals are using active monitors, that they're required to get them tested in one of the government radon chambers, for example, down in Las Vegas or in, I was going to say Atlantic City, but not Atlantic City, Las Vegas or Montgomery, Alabama, right. And they have to do that every other year. Every
2 years, active and or passive device.
Right, but the passive ones, typically they can mail in.
They can send, yeah.
And that's only if they're a primary.
Correct.
If they're a secondary, for example, putting charcoal detectors out in a laboratory is doing the analysis, then the person who's putting them into the house but doesn't do the analysis does not have to send them. The laboratory does.
They don't have to send them, correct, but they will have to now take a test as of, I believe, next month.
Right.
Which is something a little bit new.
The RMP exam.
Right.
Right. Actually, we will have an issue on that very shortly.
That's good.
So, okay, why don't you tell us how this AB5 works here and what it can do for us?
Well, this is basically, I guess, the brains of the system. This employs the scaler, and this has the timer, and this is where everything interfaces into. And then one sort of nice thing about the Pylon equipment, you can just use a lot of different attachments onto this one thing to take many different measurements. You can take this particular, what we have set up here, you can do continuous radon measurements with this, which is a passive detector. The gas just passively diffuses in here.
Okay, no pump in that case.
No pump at all. That's one thing I think we probably use this more than anything, simply because of that. We don't have to worry about any pump or flow rates or something. So it's very easy to use. You can use it with this method here, using a scintillation cell. With a method like here, it plugs into here. And you can use it in a continuous flow-through method this way, and then you do have a pump involved. You also have the working level capability here. This is a working level monitor. That's basically like the Everline unit we showed before, which once again hooks onto the front of this unit.
And then you put a piece of filter paper on that one?
Correct, filtered paper.
Okay.
And you can also use it for making grab radon measurements, once again, using the scintillation cell. Instead of doing a flow-through measurement, you take this into the house, take your sample in here for 5 or 10 minutes, get a good representative concentration of the air or sample of the air, and then once again put it on here and you just count that sample for however long you want to count it.
Okay, all right.
We can certainly show each of those methods as you want.
Well, let's start with the using it as a passive continuous monitor.
Okay. This is one of the newer models here. There's just an on-off switch here. And it comes on. It goes. And they're basically things that remain programmed in here. There's a calibration factor in here.
Okay.
I don't know if you'll be able to see that. That's the interval length, which is you have a time base here for hours, minutes, or seconds.
Right.
And that's telling you there's 1 hour interval. That's the sensitivity of the unit, which is 1.49 counts per minute per picocurie per liter.
Okay.
Which you have to determine in a chamber somehow.
All right.
And then also in there is the background.
Okay.
0.83 counts per minute.
And that number that we determine in the chamber, that's what we go to Alabama for example, every other year?
Not really, no. You should be determining this factor separately. You should not be using the RMP program as a calibration for these units.
So those calibration factors have to be determined independently of the RMP program?
RMP would like you to do that.
Right.
A lot of people probably do that. You know, how incorrect it is, I'm not really sure.
Right,
I mean,
right, right.
You're measuring a known concentration, so you certainly could do that.
Right, right. Okay. How do you get that calibration factor? I mean, you have to buy some time in a radon chamber.
Correct.
And put the monitor out there
Right.
and then let it figure it out.
And then basically what you're doing, you're comparing counts per minute that this unit displays against the radon concentration every hour. So you
Right.
compare it every hours.
So in this case where we saw 1.4, it was actually 1.44, that was counts per minute per picocurie per liter?
Correct.
So that if it's in a concentration of 1 picocurie, let me see if I have this right, if it's in a concentration of 1 picocurie per liter, it's going to show up 1.44 counts per minute.
Theoretically.
Right,
correct.
okay, okay. All right, and then now how do you fasten the detector onto this device?
One thing also, this is one of the newer models here, that this couple different modes here, continuous, radon, radon, quasi. We basically use continuous and radon. The older models just printed out just a raw number here, 100, 200, 1,000 or whatever. This will actually print out here or show in the display radon itself, so 25.6 picocuries per liter.
So right to the concentration.
Right to the exact concentration, which is sort of
So
a nice feature.
Yeah, it does the calculation internally.
Right.
Right, okay.
That's why you have to have that sensitivity in the background in there.
Sure, right, okay.
So then basically this protective cap just comes off.
And what we have here is, this is a photomultiplier tube in here.
Correct, that's the photomultiplier tube in there.
Right,
with-
okay.
And then the this adapter just basically gets screwed on there.
Okay.
And then the passive detector, and you can see there that just has some zinc sulfide inside there. And
Right.
when the alpha particles interact there, they give off the electrons.
Right.
You go like that, and then you can just start-stop button starts it, and you can see the. You
Okay.
can see
And
the
so now
spark.
air from the studio here is just diffusing into this Lucas cell of sorts, I guess.
Basically.
And as the alpha particles are emitted by the radon, then it's those alpha particles striking the zinc sulfide.
Interact with the zinc sulfide.
Right, and then that's giving off another particle that the phototube can pick up.
Correct.
And see, and those are the counts we're getting.
Right.
Is what the phototube sees.
Yes.
Right. Okay. All right. And there's probably ramp up time to this of a
Yeah,
couple
you're
hours.
looking
I
at
would
about,
imagine.
once again, this is about 4 hours. Takes
4 hours,
about
okay.
a half hour for the gas to fuse through this membrane, and then about 3.5 hours or something to come in equilibrium with the gas.
Okay. Right. Now in this one here, if we're using it in this mode for getting radon in picocuries per liter, the radon and its daughters are going to be in there. Is that right? Or is there a filter paper in there?
There is a filter,
Oh,
yeah.
I see it.
Once
Yeah,
again,
yeah, there is a filter in there.
That's a good point we should have
Okay.
mentioned. Once again, this is only looking at radon.
Just the radon, not the
Correct.
daughter products. Okay, right.
Yeah.
I didn't notice the filter paper on there initially.
All the scintillation cells would be doing the same thing, just looking at radon.
Okay.
And this would be the only thing that would be looking at the daughters.
Okay, all right. And so then the radon concentration pops out of this instrument.
Right.
Right, just like that.
And then what you can do is you can, at the end of your sampling, you can take this, basically this arrangement here into the field, leave
Right.
it in the house, shut everything down, bring it back into the lab, and just use this printer here, and the printer basically plugs into the back of the unit here.
Right.
And then you go through a little routine here, and you can dump your data out here.
Okay, so this actually has a memory in it so it can remember all the data that it's been taking.
Remember, about 600 data points.
600 pieces,
So you could
okay,
leave
that's
it in-
great.
You could leave it in the house almost a month if you wanted to.
Right, right. Okay, and now prior to using it in this mode, that is a passive radon mode, what kinds of things should we watch out for? Well, you have to check to make sure, would you check the calibration factor? You wouldn't check that.
I wouldn't check the calibration factor. We just do that basically once a year. The background, you may want to take a look at. It's a little bit more difficult to look at that because you have to find a low background environment.
Yeah.
What I primarily do is, once again, just put a standard in there.
Okay.
After it's calibrated, I run this standard for maybe 2 weeks every day.
Okay.
And then I get a range of, basically a mean and a range, plus or minus 2 standard deviations.
Right.
And I put this in there and make sure that the counts are within that 2 standard deviation value. Basically just tells me the electronics within here are working properly.
Okay, okay.
That's about the only thing that I go through
So
prior to
it's-
putting it out the field.
So in the passive, now you would call this what, a passive continuous radon?
Correct.
Okay, and so for that, it's really quite simple. You just put this detector on and really turn it on.
Basically, that's it.
And that's it. And then you calibrate it once a year, and you get it down to Alabama once every 2 years.
Correct.
To make sure that it is still running properly. Okay. Now, how do we, let's move it over to where we'd run it instead of passively, actively with a pump.
One thing, if anybody's considering buying this, they want to be careful about, you make sure you turn this off before you expose this photomultiplier to it.
Right, right.
Photomultiplier tube basically looking at photons, so it's very sensitive to light.
Right, and you can overwhelm it actually and shut it down for a while.
I've never experimented with that to see what happened, but...
Oh, I have. I've done that in labs accidentally.
Oh.
And what it does is the tube becomes unusable for an hour or two.
But that doesn't ruin it or anything?
No, no, then you just turn it back on and run it again. At least that's been my experience.
Okay.
Okay.
This is just basically an adapter for using these scintillation cells. The only difference in these two scintillation cells here is just basically the size.
Okay.
This has a little higher sensitivity. This is 271 milliliters. This is 161 milliliters.
Okay, and the increased sensitivity is just due to the increased surface area inside, right?
So this can come off.
Okay, so that's just a collar for adapter.
Correct. And then you can just hook a scintillation cell in there.
Right.
And you put the collar over to just hold,
I see.
hold it
That
there.
holds it in place.
And then, actually, there's some tubing that would run back to the pump here.
Okay,
that would
the
be
pump's
drawing
in the
air
back.
in. Well, I won't worry about that right at the moment. And then that hooks in there like that. So they're going to create a vacuum in here by the pump, and you will be drawing the air
So
through
the air
here.
comes through here across the filter
through a
paper.
filter.
Now, in this case, we're not going to be looking at the filter paper.
We're not going to be looking at the filter.
So this is just to block the daughters so that the only thing coming through is the radon gas.
Correct.
Okay. And then that gas would come out through another hose here into the back where there's another pump, and then it gets expelled.
Expelled right back into the room air.
Okay. Okay. So in this case here, now, is it important to change the filter paper before every measurement?
Once again, not critical as far as what's clean that's on the filter. Just have to watch out for loading the filter.
Right. Make sure that the filter still is allowing a flow of air.
Right. Once again, I think the same applies. Why not change the filter since,
Yeah.
well, actually they are expensive, but it's still worth it. Maybe this thing here would probably be, I don't know, $100, $200, something like that.
And how many filters do you get out of that?
I think there's probably 100 in there.
So you're talking it's about $1 to $2 a filter.
So actually they're not cheap, really.
They're not cheap. No, that's right. That's right. Wait, now how can you check the flow rate on this?
Once again, you can use a graduated cylinder. You can use a calibrated
or a flow
dryer
meter.
or something like
Right.
that.
Okay.
I guess the advantages of these two types of things, either the passive or the continuous, is you can look, you can track the concentrations over time. You can look at the fluctuations, see what's happening. We use these for lots of times diagnostics.
Sure.
When you see a heater comes on, you can see the spikes and so forth. You get snowfall, something like that. So it gives you a lot of data that something like a charcoal canister or some of these other devices, like an e-perm, would not give you.
That's right. Yeah, charcoal canister gives you one measurement. That's it. A reasonable average over a given period.
Here you'll get 48 or 60, and you put them on your PC, and you have a very nice graph.
Right. Right. Okay. All right. And then and this operates the same way you would do the start it the same way.
Everything else is the same, except you're just pulling air through.
Right, okay.
And the other thing you could do is you don't have to have this on there. So that would be the continuous flow through. And if you wanted to use it in a grab sampling method, once again, you could basically work the same way here. And the air pump would be connected here, which we don't have it right there, and you'd be in the basement and you just take a grab sample of radon.
Okay, and you could grab for, how many minutes would you do a grab sample? Maybe 5 minutes?
We usually do 5 minutes. Now this is what you would certainly be using more so for diagnostics.
Right, again you can't report that to the homeowner with the intent of having some mitigation done.
Whereas if you wanted to do diagnostics, for instance, and you can put a tube on here, for instance, and then use this to go in different places that are inaccessible inside a hole that you've drilled in a block wall, down a sump hole, anywhere you want, basically.
Now, let's talk about that, because suppose you use this initially and we go into a block wall, for example, and we draw off some air from inside the block wall to determine the radon concentration. Now, can I use that cell again? So I take the cell, I put it on here, and I get a number of counts per minute, or actually a radon concentration?
Well, you probably won't get a concentration. You'll just get raw counts is what you're usually looking at in the sniffing type of mode.
Right, and all right, so then you might not even convert that to concentration.
You wouldn't have to, no, because you're just getting some raw numbers when you're sniffing like that.
Okay, now would you then say, could I take the same cell and say, well, now I've drilled another pilot hole into the slab and I want to draw some air from out from under the slab. Could I use the same cell right away?
You could, but what you probably want to try to think to yourself is, try to start with the lowest concentrations first, or where you might expect to see the lowest concentrations first. Certainly under the slab, you'd expect to see very high concentrations.
Right, right.
So maybe I'd start in maybe just ambient and take a sample, because you certainly would have this cell contaminated.
Right,
if
and it
you
might
took
stay,
a high, and it might stay contaminated.
Right, and then so if you took a high one first, then you really couldn't use that Lucas cell for, that scintillation cell for a second measurement in short order. You might have to let that sit for a day or two.
It would very possibly overestimate, yeah.
Right, so you really ought to have 2 or 3 of these cells if you're going to
definitely.
go do some diagnostic
Definitely.
work. Right,
and you also want to, you should probably flush them out in between measurements. Just go outside and flush it for 5 minutes or something.
Right.
And they come down. They come down pretty quick.
Yeah. Okay. Okay. And now, all right. Now we have one
more, I guess.
One more device. This pylon is also very capable.
Yeah.
I don't know if I mentioned, but this pylon device, I think with some of these accoutrements, runs about $3,700.
Now that would just be for this unit itself.
Oh, that's just this unit itself.
Yeah.
Oh, and then you pay more for the rest, for the other parts.
Everything's extra.
All right. So you're talking somewhere in the order of $4,000 and up to get this system operating.
And then the final attachment that we brought along here is just for the making the working level measurements. This, once again, this would be a continuous working level, just like the Eberline. And it comes off, and a piece of filter paper is brought in there.
Okay.
And the retaining cap is put back on. And this is put in the exact same place that all the other attachments are put.
Okay. And then air is drawn through here?
Correct. Then you just attach a piece of tubing to there, and then to the back of the pump here.
Right.
And that would create the airflow flue here, and the air would be traveling through there.
Through here,
onto the filter paper.
And then out.
And it interacts with the
okay, now what's on? Oh, now what's on the filter paper? Oh, there's a zinc sulfide inside this portion too.
And that's in contact basically with the photomultiplier tube.
Right. So again, the filter paper has the daughters. The daughters decay by the emission of the alpha particles. Those alpha particles strike the zinc sulfide.
Right.
And then the photons that come off from that are seen by the phototube.
Right.
Okay. All right. Now, one thing that I'm curious about, if we put the filter paper on here, the daughters are going to be collected on this side of the filter paper, and the alphas that are emitted, not all of them will make it through that filter paper, will they?
Probably not. It's very thin filter paper. I don't have any with me.
Oh, okay.
But you're going to obviously get emissions in both directions for
right,
one.
right. And you're only going to get the ones that make it through that filter paper and strike the zinc sulfide.
So, and once again, in this method also, an efficiency has to be determined.
Right.
There is a method that they give you where you actually plate out some daughter products onto a filter of exact same nature that you're using, and then you can calculate the efficiency by that method.
Oh, I see. And do they give you, I guess you can buy the source of the daughter products?
Yeah, there's a standard that they give you.
A standard you can use for that to get
basically
the efficiency.
I did not bring it along. You put a filter paper at the bottom of a little disc, and the daughters actually drop onto the filter paper itself.
Okay, all right.
And you just take the filter paper out and place it in here and do a count.
Okay, and that's how you determine the efficiency. Now, how often should you do that if you're going to use it in this mode?
I honestly forget that offhand. We very seldom use this mode. We sort of favor the Eberlines.
Okay.
They're just seem to be a lot easier to use.
Right, right.
So I haven't done this measurement in such a long time. I don't remember what they're recommending for that.
Okay. All right, and in this mode here, it would be listed as a continuous working level monitor. Is that correct?
Correct.
Okay, continuous because we can let it run for long periods.
Right.
And working level because we're looking at the daughter products.
Correct.
And then we can get the data out 1 hour at a time if we want, plus some average value over the whole time period.
Well, this does not give you an average as the Eberline does, so you'll have to do that on your PC or the calculator.
Oh, I see, okay.
It just gives you the raw data, 25, 50, whatever.
Right, on an hourly basis.
On an hourly basis, or any time basis
whatever
you want.
interval you set in.
Yes.
Right, okay, all right. This too has a lot of capabilities. Now, I think that's just about all of the equipment that you brought down for us, right?
That was all, with the exception of this one other monitor, this at ease monitor. And the only reason I basically bought this is because this is much lower end price than all these things we've been showing.
Right.
So for somebody, maybe mitigators or something that want to do something, they could certainly look at something like this.
Right. Now I think this runs about $300–400, somewhere along that order. These other active monitors are running in the thousands.
All into the thousands.
Right.
Yeah.
And this runs into the hundreds.
Correct.
Fundamentally. Now, how long can you let this operate if you put this into a house?
Well, this is basically a continuous radon monitor.
Oh, it's a continuous radon monitor.
Yeah, so you can
okay.
just leave it in, minimum of 48 hours up to whatever you'd like.
Right, right.
And
And you were explaining to me earlier that if you read these little lights,
Yeah.
the little lights that you see here, somehow by
This is a little awkward for that matter. These lights will give you an indication depending on which one displays first,
Right.
the concentration. Some of their newer models actually have an LCD display up top.
which give you the radon concentration, right?
Yeah, there's two buttons. You can either press a present, I think, which gives you the concentration at now, or an average button, which gives you the concentration over the time periods you've been sampling
Yeah, it
from.
seems like that would be a little more convenient.
Quite a
Right,
bit more.
Right. Yeah, and I don't think that's a lot more expensive, actually. I still think that runs around $300-400.
I think they're a little bit more than that. I think they're more $700 or $800.
$700 or $800, okay.
And they give you
All
some
right.
printer capabilities too, which I think may
okay.
even plot your data out.
On a
Also,
regular
I haven't
basis.
seen I haven't seen the
All right.
newer models.
So this being a continuous radon monitor, does it have a pump in it when it's running?
No, it's just diffusion.
Oh, it's just diffusion and in through the top, apparently.
Correct.
Right. And I see there's a big piece of filter up here, some kind of fabric, actually. And is that used to prevent the daughters from diffusing through?
I'm not sure what that functions as, to tell you the truth. I don't know if that's we're using it as a filter or not.
Yeah. It looks pretty porous. I don't know either.
Yeah.
I don't know either.
Um,
Okay, well,
we just basically have it. We don't really use it.
Yeah, yeah. If you want more details about the Honeywell monitor, you should contact the Honeywell people, I guess.
Certainly.
Okay, and I think that's about it.
I think that's about it, yeah.
Okay, great. Listen, thank you very much for coming and spending a good part of your morning with us. And I know you've got a good-sized drive back today as well. So, Bob, thank you very much.
I'm glad to be
Appreciate
here.
it.
Thank you.
You're welcome. Hopefully now that you've seen some of the equipment, these protocols will be a little more meaningful. So we start with our protocol considerations and a summary of those protocols. Now there are three parameters of interest that are discussed in the protocols. Well, at least the first two are discussed, precision and accuracy, and I've tossed in the one on bias because I think that's an important one as well. Now, as you see here in this visual, precision is the ability to arrive at close to the same value with several measurements. That doesn't mean they're right. It just means that the values are close to the same value. Accuracy is the ability to get the right answer. So bias is the effect of high precision. That is, you're always getting pretty much the same answer, but it's always wrong by the same amount. And that's what we call bias. Now, in this particular visual, I have seen this in earlier work. A bullseye is presented, and there are three sets of measurements that are made, each set being 4. Now, the measurements labeled O that you see here, you'll notice, are away from the bullseye by always the same amount. And we're taking the bullseye as being the correct value. That is, if the bullseye represents 10 picocuries per liter, that is the correct value. And you'll notice that the O measurements are always off by the same amount. Now, they have high precision because they're always about the same value, but they're quite a ways away from the correct value and always by roughly the same amount. And so the O's we would call high precision, poor accuracy, and positive bias. They're always a little too high. The way I've drawn it here, they're always a little bit too high in value. If you take a look at the B's, the B measurements, there are 4 of those, and all 4 B measurements are on the money. They have the right value. They're on target. And so those 4 B measurements have high precision because they're grouped together, and high accuracy because they all get just about the same value. If you look at the A's, there's one up here, down here, over here, and over here. These have crummy precision because they don't even reproduce the same value, and poor accuracy as well. They don't even come close to the bullseye. Now, the average of those 4 might come out to be an average value close to the bullseye, but that doesn't matter. We're concerned about precision, dealing with the grouping of the values, accuracy being getting into the bullseye, and bias, as we see in this example here. So the A's would be listed as, frankly, crummy all the way around. Poor precision, poor accuracy, and no reasonable bias either. They're just all over the place. Let's take a few examples of this. Consider 4 detectors placed in a radon chamber whose concentration is 10. That is, we know the chamber is set to 10. And suppose we get the values listed here. 15, 15.1, 14.9, and 15. Now this is high precision because the values are all close together, but low accuracy because they're 50% away from the correct value. And a positive bias. They're always to the right. They're always a little bit on the high side. So positive bias. As another example, numerical example, if the values were 9.9, 10, 10.1, and 9.8, now notice this is high accuracy, assuming the chamber is set to 10. This is high accuracy, high precision, no significant bias. One final numerical example, if the values are 11.4, 11.5, 11.3, and 11.5, as you see here, then this is positive bias. Remember, the chamber is set to 10, so this is a positive bias, always a little bit too high. High precision, those values are all close together, and fair to modest accuracy, they're all about 10 to 15% off. So that would be fair accuracy. So that's the distinction between the three terms that I would like you to remember. If you'll take a moment now, what follows on the next page is a set of questions, and if you deal with those questions as we have in the past, return to the video at this point. Again, I hope you've gotten all the right answers to those questions or worked your way to the right answers. Let's take a look at some information that is true in general for all of the protocols. In this visual, you see, in general, the minimum measurement time is 48 hours with a 2-hour grace period. Now, the purpose for a 48-hour minimum measurement time is simply this, that we have seen earlier that the radon concentration varies tremendously from hour to hour and day to day. So to get a reasonable average over diurnal fluctuations, a 48-hour measurement is required. So if you put a detector in at 10 o'clock this morning in someone's home, you can pick it up at 10 o'clock 2 days later. But suppose 2 days later you go over there and it's 9 o'clock. Oh, well, what are you going to do? You're going to wait around for an hour to pick it up? So that'll be 48 hours. The answer is EPA says no, you don't have to. They're going to give you a 2-hour grace period. So you can pick it up as much as 2 hours earlier. So you might think, so the minimum measurement time is 46 hours. That is not true. The minimum measurement time is 48 hours, and there is a 2-hour grace period. Furthermore, we see on this visual that short-term measurements should always be under closed house conditions. Now, closed house conditions, again we've discussed before, should be done for 12 hours prior to the measurement and also during the measurement. This is true in all the protocols. If you're going to do a short-term measurement, this is required. Now, there are a few specifications and some wording that is important here. Measurements lasting less than 4 days must be closed house conditions, must be made under closed house conditions with that 12-hour requirement before and for closed house conditions. And of course, closed house conditions must exist during the measurement. However, for measurements between 4 and 7 days, it is strongly recommended that we have closed house conditions for 12 hours prior and during the measurement. So for between 4 and 7 days, it does not say must, it says strongly recommended. Now that, in a sense, makes sense. That is, if you have the longer the measurement, the less impact the first 12 hours are going to have anyway. And so the shorter the measurement, the bigger the impact 12 hours prior to beginning will have. So I think you'll need to remember this, that if it's less than 4 days, that you must have 12 hours before. If it's between 4 and 7 days, then it's strongly recommended that you must have closed house conditions for 12 hours prior and before. Now, what kinds of things can operate when you're doing a measurement? Again, this is true for all of the measurement devices. It's okay to operate ear-to-ear heat exchangers, permanent radon mitigation systems. The idea being that these things should be operating in the typical daily activity of that house. It is, however, not okay to operate attic fans, window fans, if you had a whole house ventilation fan, those things were not okay to operate. Again, continuing on with the protocols for all measurements, the measurements should not be done if you're going to do a 2 or 3 day measurement that is relatively short term, and I have to say this is the majority of measurements, 2 or 3 day measurements, you should not do it if the winds are more than 30 miles an hour. That's a key number, 30 miles an hour. You want to underline that. The reason being, of course, high winds cause low pressures, and that enhances the amount of radon coming into the house, and that would give us anomalous values for radon concentrations. That is not indicative in any way of an annual average. And you should not perform these short 2 or 3 day measurements in rapidly changing weather. Again, rapidly changing weather means a rapid change in atmospheric pressure. Obviously, you cannot make these kinds of constraints on longer term measurements. If you're going to do, say, an 80-day measurement, which is still considered short term, anything between 2 and 90 days is short term. If you're going to do an 80-day measurement, you have no control over the weather or the winds, and no way to determine whether or not the weather or the winds are going to be greater than 30 or low atmospheric pressure conditions. So this is only for 2 or 3 day measurements. Also, in each of the protocols, closed house conditions must be verified. Must be verified. I underline that. And the reason, now what that means is somewhere in your log of what you have done at that particular house, you must write down that when you left that house, the closed house conditions were met. Or were not met, perhaps. Bearing in mind, of course, you're supposed to make sure that they are met. But that must be logged, that must be verified. Also, in all of the protocols, no measurement is to be 20 inches above the floor, less than 20 inches above the floor. All measurements are to be at least 20 inches above the floor, regardless of the detector type, whether it's a charcoal canister, the E-perm, etc. Regardless of that type, the location must be at least 20 inches above the floor. And we've seen this before, not near drafts, not within 3 feet of windows or other potential openings. Now, remember, potential openings. This could be things other than windows. It could be fan outlets for bathrooms, kitchens, etc. Not near high temperatures or humidities. These things, these locations constraints are true for all the protocols, for all the devices. Here's one you will never forget now, at least 20 inches above the floor. You've seen this 3, 4, 5 times so far. If the device is hanging, and you can hang devices like E-perms, Alpha Tracks, potentially you could hang a charcoal can, although they're generally not designed to do that. If it's a hanging device, it's to be hung 6 to 8 feet above the floor. The idea here being that it should be in the breathing zone. Now, this will be in the breathing zone, of course, if your height is 6 to 8 feet. Now, I'm not 6 feet tall, so 6 to 8 feet would never be in my breathing zone. Nevertheless, the protocols state that if it's a hanging device, that it's to be 6 to 8 feet above the floor, and at least 4 inches from other objects. Now, you want to keep it from other objects, away from other objects, because you want a sample of the ear in the room. And if you put it between 2 books, for example, then you'll only get a sample of the ear between the books, and that ear will not be exchanged as readily as the ear in other parts of the room. So at least 4 inches from other objects. In the area of documentation, what kinds of things do we need to write down? Now, if you just think to yourself, what things should I write down when I bring the detectors into the house? Well, obviously, start and stop times. You have to know this. For every device, you must know the start and stop time, as when you deployed it and activated it, and when you picked it up and stopped it from being active. You must also document whether or not standardized conditions were met. That is, did you have closed house conditions for 12 hours prior, if that's required? Compliance with standardized conditions. The exact location of the device. Now, you might think if you drop it off in a house that you'll remember where it is. But if you drop off 5 or 10 in a given week, and you pick them up early the next week, I think you'd like to know exactly where you put it. And was it on top of that file cabinet in the basement rec room, or was it on the coffee table in the living room on the first floor? You should write that down, where it is, where the location is. What other things should you know? If you think about this, the other things you should know the serial number, because lots of laboratories will report values based on the serial number of the device. So you're going to have to relate that serial number to where and in which house that was placed, and the manufacturer of the device. This you might not think you need, but the truth of the matter is you do need to remember it. Now, also other information should be jotted down in your log. And that other information, for example, whether or not there's a crawl space or a basement, the condition of the basement or crawl space vents, and the operation of any air-type devices. Is the individual running, say, a wood stove or a coal-burning stove that vents a lot of inside air to outside to pressurizing the building? These things that we have looked at so far are common to all of the measurement devices. And having said that now, the next page in your book is again a list of questions, and I'd like you to deal with those questions right now as you have in the past, and again return to this part of the video. Hopefully you again have gotten all the right answers or worked your way through the right answers. Let's move along through the protocol summary now and discuss the considerations called quality assurance. As you can see in this particular visual, the purpose of quality assurance is to give confidence that the results that you get have good accuracy and precision, and good precision with no bias. That is, you want to do the same things the same way that work over and over again, and you want to check to make sure that it continues to work. Now, one of the things that you need to check are called instrument calibrations. These are predominantly for active systems. For example, if you're using a grab sample device, or with a photo tube and some other lab equipment, for example, or if you're using an EPERM unit with a voltmeter where you're going to measure the voltage on the electret. For any of those things, you're to get the instrument, the laboratory component, in this case it would be the voltmeter, the electrometer, you're supposed to check that at least once a year, and that's what you see listed here in this visual. Instrument calibrations once a month, once every 12 months, excuse me, once every 12 months. Once a year. And that really is a minimum amount of time to make sure that the thing is still working right. And also note on the visual, I point out that the RMP program, for those of us using active systems, RMP program does not qualify as a calibration measurement. Now the RMP program is where you take your electrometer or you take your laboratory equipment down to one of the radon chambers that the EPA has, and you show them that you can come up with the right result. Now you would think that that could be used as a calibration, but currently the EPA does not permit that to be considered as a calibration. So remember that the RMP program does not qualify as a calibration technique. Now there are three other things here: spikes 3%, dupes, and on the next visual we'll see blanks. But for now let me just talk about what a spike is. Part of your quality assurance, part of your procedures which will assure you that you're getting correct results, is to perform these spikes. And of course it points out that the spikes are to be done at 3%. And that's 3% per month. So if I'm using charcoal canisters, for example, and I put 100 of them out in a given month, I have to spike 3 of them. That is, they don't go to the home. What a spiked is I take the canister and I send it to a radon chamber. And at the chamber, the concentration, of course, is known. Suppose it's 20 picocuries per liter. And we put it in there. And then after the appropriate exposure time, that's sent back to the lab. And the lab should come up with the right answer. In other words, you're checking to make sure that the process works. And of the spikes, you're to do, as you see, 3%, that's per month, 3 out of every 100, with a minimum number of 3 per year. So even if you do none in a given year, you must still do 3 spikes, and you must do a maximum of 6 per month. So if you're doing, let's say, 600 in a given month, 3% of that would be 18. But you don't have to do 18 spikes, you only have to do 6. Now you're going to see this for just about every device protocol. Spikes are done at 3% with a minimum of 3 per year and a max of 6 per month. Another component of your quality assurance is going to be duplicate measurements. Now, in a duplicate measurement, what you will do is you go to a home, and instead of deploying one detector, again, if you're using charcoal cans, instead of deploying one can, you'll put two cans side by side. That's a duplicate measurement. You treat them identically, you send them back to the lab. And the duplicate should be done 10% of all your measurements on a monthly basis, or 50 per month, whichever is smaller. And this is nice of the EPA in the quality assurance plans, that it's always whichever is the smaller. So it's 10% or 50 per month, whichever is smaller in duplicates. Also, you're to do routine instrument checks, as you see here. Now, depending on the instrument you use, routine instrument checks are different. If you're using, for example, a continuous working level monitor, as we saw earlier, there's a filter always. Well, a routine and a pump, typically. And so in a routine instrument check there, you want to check the pump, check the flow rate of the pump, change the filter. And if you think physically of what actually goes on with that instrument, you can think through what these instrument checks should be. Also, as part of your quality assurance, you will do background measurements. And in this visual, let me go right to field backgrounds for a moment. We'll come back to the others in a second. If you look at field backgrounds, this too belongs to the technician. And what a field background is this. You will take your charcoal canister, again, if that's what you're using, you take your charcoal canister, and instead of deploying it out in the building or out in the field anywhere, you're simply going to send it back to the lab. It's a blank. It's never been used. And so the lab ought to return a value below their lowest level of detection, below their LLD. And typically for charcoal cans, that is 0.5 picocuries per liter. And so they should return a result lower than 0.5. If they returned a result of 2.4, that would tell you there's something wrong in the system. Either the charcoal can was not properly sealed, or their laboratory is not working properly. In any case, dupes are to be done at the rate of 5% on a monthly basis, or 25 per month, whichever is smaller. Now, if we think about this for a moment, we have spikes at 3%, dupes at, field backgrounds at 5%, and dupes at 10%. How are we going to remember this? Well, the way I remember this is this. The spiked ones are going to cost money. You're going to have to rinse space in a radon chamber. And so the percentage required is small, 3%. Blanks you have to pay for as well. You still have to pay for the detector, but you don't have to pay as much as renting a radon chamber. So there the percentage is a little higher, and so for blanks we're talking 5%. Dupes are measurements placed side by side, duplicate measurements, and they check, of course, on the precision of the lab. Those, at least you're getting some money for that, because when you deploy them, you're getting paid for at least one measurement. And so that, the percentage is made higher, 10%. So it's 3, 5, and 10, and I think if you remember which ones cost more, you can pick out which ones go on to 3, 5, and 10%. Also recognize that that's a total of 18% of all your measurements are for your quality assurance out in the field. And that sounds high initially, but I've conferred with a number of laboratories, and the labs tell me that their quality assurance plans generally require that 30% of all their measurements are part of their quality assurance plan. Effectively, every third measurement they do is part of their QA plan. So this 18% is not excessive in that light. Now, if you're using continuous monitors, the number of background measurements you should make should simply be a statistically significant number. Now, what that means is, to some degree, unspecified, and so simply a statistically significant number. I'm not going to give you a number by which you can guide yourself. Ask the manufacturer of the device, what's a statistically significant number? For passive detectors, in the lab, the laboratory has to check its own background. How many? A statistically significant number, again. So you'll want to remember that laboratories must do blanks. They're called lab blanks, a statistically significant number of them. If using continuous monitors, again, a statistically significant number. But out in the field, the number of blanks or field background measurements is to be done at 5% or 25 per month, again, whichever is the smaller. Now, I'm going to summarize the protocols here for you to some degree. And in the area of results, there's a parameter called the LLD, the lowest level of detection. Now, what that number represents is that the laboratory is confident, or reasonably confident, that down to some low value, they are still reading correct values. For example, if you take a look at the EPERM, if we deploy this in a 50 picocurie per liter environment for a given amount of time, the laboratory will be able to read that pretty easily. And you'll be able to calculate it using the electrometer, for example, quite easily. If we lower the concentration to 1 picocurie per liter, can you still read that easily? That gets a little more challenging. What is the lowest value that we can read, say, with the electrets here, and still be quite confident? Well, we're told, as you see in this visual, that for electrets, the value is between 0.2 and 0.3 picocuries per liter. So they can read down to this level with confidence that they're getting the right value. Activated charcoal, that is the canisters, can read down to 0.5 picocuries per liter. Typically, except for these two and one other notable one, typically LLDs are less than 1 picocurie per liter. Almost every device can read to less than 1 picocurie per liter. Now, one other device which is unusual in some respects is the grab working level device. And we saw that operate in an earlier part of the video with Bob Lewis from the Pennsylvania DER, who showed us that. And they have an ability, those have an ability to read down, as you see here, since they grab working levels, 0.0005 working levels, which at a 50% equilibrium ratio is equivalent to 0.1 picocuries per liter. So they can read down to what seems to be about the lowest value available. But don't forget that grab working levels do not satisfy the constraint of the 48-hour measurement period minimum. Let me say one more thing about that 48-hour minimum while I'm here, and that is you can make measurements less than 48 hours, but you're not permitted to report those to the homeowner with the intention of the homeowner using that data to decide on whether or not a mitigation system should be installed. You might use a grab working level monitor, for example, to determine whether or not a particular part of a house has a lot of radon in it, maybe a sump hole that may have maybe the source of the radon in the house. You can do grab working level measurements for that. You just can't use excuse me, those kinds of results to give to the homeowner to determine mitigation systems. I want you to remember the minimum measurement period is still 48 hours, 2-hour grace period. Minimum is 48 hours. These very short-term measurements can be used for diagnostics, and fundamentally that's about it for the use of the short-term measurements. Coefficients of variation. Here, continuing on with this visual, coefficients of variation, typically they are at 10% at 4 picocuries per liter, which again at the 50% equilibrium ratio is 0.02 working levels. Now what this means, what is a coefficient of variation? Well, there's a fairly cumbersome formula that you can use to determine a coefficient of variation, but fundamentally, to a reasonable degree, if I put two duplicate measurements out, they should be within 10% of one another at as low a concentration as 4 picocuries per liter. So if this gets a concentration of 20, and the next canister right beside it, that other duplicate, that other part of the duplicates, reads 19. This is 20, that reads 19. They're within about 5% of one another. That satisfies the 10% requirement at 20 picocuries per liter in that case. And that same kind of close value relationship between the two duplicates should exist at 4 picocuries per liter as well. Now, what I would like you to do is the next thing that follows in the packet that you have in the visuals is the table that I have summarized all the protocols with. And I want you to spend a few minutes just looking over that table, noting the percentage of spikes, dupes, and blanks that are supposed to be done for each different device type, and note the comments that have been made under the column titled Other. Things, routine instrument checks, etc., etc. And just spend a few minutes looking over those things and see if they confirm the information I've already given you. And of course they will. But that will help reinforce it in your mind. After that, you will see a host of questions. And I'd like you to answer those questions and then return to the video at this point, and I'm going to demonstrate a few of the calculations that are performed in determining radon concentrations. Okay, so if you'll do that now.